Good morning. All right, today we're going to look at a packet, chapter 10. This is page 288. 288 all the way to 293. It looks like a lot of pages, but we'll get through them fairly quickly. Some of these are really quick. And there's first a discovery activity. So we're going to graph some things and kind of look at end behavior of functions and different behaviors of polynomial functions. Imaginary roots will always occur in pairs, okay? What that means, and not just pairs, but specifically complex conjugate pairs. So when you think about solving quadratic formula, x equals opposite b plus or minus square root b squared minus 4ac all over 2a. Okay, if you get an imaginary number, the reason it's imaginary is because you had a negative under the radical. Okay, let's say you had a negative 4 under the radical. That it turns into plus or minus 2i under the radical. So you get a number that's not imaginary plus or minus a number that is imaginary. Okay, complex conjugate pairs are things like 2 plus I, 2 minus I. Okay, 1 plus 5i and 1 minus 5i. Notice they will always come in pairs if there are solutions or roots that are solutions to the quadratic equation. Okay, if there's an imaginary number or an imaginary part, that's always going to have a plus or a minus in front of it. These two are complex conjugate pairs. These two are complex conjugate pairs. If a polynomial is at the n degree, there are n roots, okay, including both real and imaginary, also including double roots. If it's a double root, we count that as 2 when we're talking about the degree. So if it's 5th degree, we need to be looking for 5 roots. Some might be real, some might be imaginary. Okay, if 3 plus 2i is a root, then 3 minus 2i is also automatically a root, again, because they come in complex conjugate pairs. So if there's a plus in front of the 2i, there's going to be another root with a minus in front of the 2i. What is end behavior of the function? Well, it's really what's happening to your functions at the ends. What happens, it is what happens to your function. What I mean to your function, the y value of the function, which is the value of the function, as x goes all the way to the right, so we say to the right means towards infinity, and as x goes all the way to the left, which is negative infinity. Okay, now graph these 4 on your calculator. If you want, you can pause this, grab each of these 4, and determine the end behavior. As x goes off to the left, what's happening to y? As x goes off to the right, what's happening to y? Okay, pause now if you want to go ahead and do that, because now I'm going to go over them. So I'm going to show you, I actually already graphed these. So if you look at the first one, this is 4x. Oh, this is not the first one. This was supposed to be the first one. Let me fix that. That should be 4x squared minus 3. Okay, that didn't work. 4x squared, and enter. Okay, so that's a parabola, which means as x goes off to negative infinity, we're talking about the left side of this graph. As x goes off this way, my y value is going off to infinity. Okay, and as x goes off to the right, to positive infinity, my y value is also going to positive infinity. Okay, so on the left and the right, we're going off to infinity. Our graph looks up to the left and up to the right. This is an abbreviated way to say this. Okay, the next one, y equals x cubed minus 2x minus 2. X cubed minus 2x minus 2, I graphed this one correctly. As x goes off to the left, my y is going down to negative infinity. As x goes off to the right, my y is going up to positive infinity. So filling this in, as x goes to the left to negative infinity, my y was going down to negative infinity. And as x goes to positive infinity, my y was going to positive infinity. So on the left, you're going down. On the right, you're going up. So this is another abbreviated way to say that, okay? The next one, x to the 4th minus 2x squared minus 2. Let's take a look. That one here, x to the 4th minus 2x squared minus 2. On the left, your y value is going up to positive infinity, and on the right, also up to positive infinity. Okay, so these are both going to positive infinity. That was up and up. Now this one, x to the fifth, is the fifth degree minus 3x cubed minus 2. And that's the next one. X to the fifth minus 3x squared minus 2. On the left, as x goes to negative infinity, y is going to negative infinity. As x goes to the right, y is going to positive infinity. So this is down and up. So down and up, down on the left, up to the right. So as x goes to negative infinity, my y is going down to negative infinity. And as x goes to the right, positive infinity, my y is going up to positive infinity. Okay. Now, which of these are odd degree functions? So we look at the highest degree term. Okay. The odd ones are 2 and 4. Which one are even degree? That's second degree and fourth degree, so 1 and 3. What do you notice about the end behavior of the even degree functions? Okay, the even degree functions were 1 and 3. So 1 and 3, they were both going in the same direction. So that's this one and this one. Okay, so your end behavior, I'm just going to write up and up. Okay, odd degrees, so this one up here, third degree and fifth degree, they were down and up. Now I'm going to make one more distinction here. The lead coefficient for all of these is positive. Okay, so your lead coefficient, the term that has the highest degree, okay, the lead coefficient positive 4, positive 1, positive 1, positive 1, they were all positive. Okay, now take each of the functions in 1 through 4, make the a term negative. So we're going to change each of these so it's negative. And what happens? Let's look at what happens. Okay, so let's go back to the first one. We change this one, make that lead coefficient negative. Now look, the end behavior is up and up. What happens when we change this to a negative? Okay, now it's down and down. Okay. So let's look at the other even degree function, which was number 3. Oh, that was number 3. Okay, let's look at the first one. When we make this end behavior negative, so this was the first one, make that negative, and behave. So this one is down and down, and I already did the third one. The third one, this one also changed to down and down. Okay, so if you change the lead coefficient to be negative, now your end behavior is down and down. Okay, so even degree positive lead coefficient was up and up. Even degree negative lead coefficient was down and down. Okay, let's look at these. The odd degree functions, well, that was numbers 2 and 4, the third degree and the fifth degree. Let's make those two lead coefficients negative. So that was the second graph. I'm going to make that x cubed negative. Notice on the left, this is down. On the right, it's up. So if I make the lead coefficient negative, that switches. On the left, we're up, and on the right, we're down. Let's see if the same thing happens for the fourth graph, okay, for the other odd degree function. Okay, now it's down on the left, up on the right. If I make this negative, enter, now it's up on the left, down on the right. Okay, so there's a pattern. So if the lead coefficient's negative and it's odd degree, now instead of being down on the left, up on the right, it's now up to the left, down on the right. Okay. Now, the easiest way for me to think about this, I think about the easiest even degree function I know where the lead coefficient is positive. So that's something like y equals x squared, which I know is a parabola opening up. It's up and up, okay? If it's even degree and a negative lead coefficient, think about y equals negative x squared. That's a parabola opening down. So you would have down and down because you have something that looks like that. Okay. Odd degree function, the easiest possible odd degree function you know is y equals x, x to the first, that's odd. The lead coefficient's positive. The coefficient of x is positive. That's just a line with a positive slope. On the left, you're down. On the right, you're up. And then the easiest odd degree function with a lead coefficient that's negative is something like y equals negative x, which is a line with a negative slope. Just up on the left side, down on the right side. Okay. So instead of memorizing this table, I kind of relate it to the easiest functions I know that satisfy those criteria. Okay. Let's go to the next function. Sketch the graph of this. Now this one we already sketched. Okay. This one was, and we can use our calculator for this one. I think this was the second one, right? X cubed minus 2x minus 2. Let's change that lead coefficient to be back to positive. Okay, so you can see the y-intercept is 2, but it's going to look negative 2. It's going to look something like this. What's the degree of this function? The degree is 3. So what is the maximum number of turns on this graph? Okay, well, let's just say, let's look at how many turns there are on this graph. A turning point is when you change from going increasing to decreasing. Right there, that's a turning point. Turning point. This right here, where you go from decreasing to increasing, that right there, that's a turning point, TP. Those are your turning points. There are 2, okay? At most, there will be 2. There might be 0. Think of the function y equals, actually, I'm not going to use that. I'll come back to that, okay? Now let's look at this one. X to the 4th minus 2x squared minus 2. Let's go to our graph. That was the third one, I think. X to the 4th minus 2x squared minus 2. We had a positive lead coefficient. Let's change that back. Okay, now notice, and behavior's up and up. We've got 1, 2, 3 turning points. Okay, so we're not being super detailed right now with these graphs. But you've got a turning point there, you've got a turning point there, and you've got a turning point there. So this is 4th degree, x to the 4th, and there's a maximum of 3, okay? So what do you notice about the degree of the function and the maximum number of turning points, or sometimes they're called bumps, okay? Turning points or bumps that appear in your graph. Well, hopefully you noticed, and this is a pattern that actually holds, the number of turning points or bumps, I'll say the maximum number, because sometimes it's less, and we'll see some examples. The maximum number of turning points or bumps is 1 less than the degree. Oops. Of the function. Okay. So if it's something 6th degree, it could have 5 bumps or turning points. If something's 8th degree, it could have 7. Okay. We'll look at that more with some of these examples. Okay. Now, the point of all this is that hopefully we can analyze these graphs and we can start to graph them without a calculator by analyzing different properties of the graph. Okay, find the zeros of this by factoring. Okay, if we set this equal to 0, we get 0 equals, that's going to be x minus 2, x minus 5. So we've got 2 zeros. One of our zeros is at 2, one of our zeros is at 5. Those are our x-intercepts, 2 and 5. Do we know our y-intercept? We do. If you plug in 0 for x, you're going to get 10 for y. Okay, let's call that 0, 10. Excuse me if that's not quite to scale. Okay. Now from the degree of the function is 2, x squared. Maximum number of bumps is 1 less than the degree. Total number of zeros matches the degree, so that should be 2. Total number of real zeros, well, we don't know that until we figure out the zeros. 2 of these are real. That accounts for the total, which means there are no imaginary. If we know there's a total of 2 and 2 are real, then there can't be any imaginary. Remember, the imaginary ones, the complex ones, will always come in pairs. Okay, so we can graph this. We know that The end behavior, because it's even degree and it's a positive lead coefficient, we know the end behavior is up and up. We also know we've got to pass through these 2 points and then pass through the y-intercept. Okay. Second degree, so at most 1 bumps, and there's our 1 bump, or turning point. Let's look at the next one. Find the zeros or roots of y equals x squared minus 4x minus 4 by factoring. So 0 equals x minus 2 times x minus 2. Okay, that's a little tricky. So we've got x minus 2 squared. The degree of the function is 2, which means the total number of zeros is also 2. Maximum number of turns, 1 less than the degree, so 1. Total number of real zeros, this is tricky. It looks like there's just 1. Your 0 is 2. But since this is a 0 of 2 that occurs twice, we call it 2. That accounts for 2 of the zeros of the function. So remember, we have to account for 2 because it's second degree. They're both real. There's no imaginary ones here. Okay. Now, what happens on your graph for something like this? Well, if we put this into vertex form, we know our vertex is at 2, 0. Our y-intercept is 4. Lead coefficient's positive, and it's even degree, so we know our end behavior is up and up. Okay. So, but since we know this is the vertex, we know that it goes up from there. Okay. This is called a bounce. It's almost like your graph wants to cross the x-axis, but at the last second turns around the other way. Your turning point is actually on the x-axis, or your graph bounces off the x-axis. That happens when there is a double zero. There's a double zero because you have x minus 2 times x minus 2. It's like you have a zero that occurs twice. Okay. There's a bounce when there is a double zero at x equals some value. Okay, say x equals a. Here it's x equals 2. Total number of complex 0. Well, there were 2 total. Both of them were real, and so there's 0 imaginary. Okay, let's go to the next one. Find the zeros or roots of this thing by synthetic division. Sketch the graph below and label the roots. This will be a nice review. Remember how we figure out if something's a 0? Our possible zeros are all the factors of 12. Factors of 12. I won't list them all. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Okay. I actually took the liberty of testing. P of 2, I believe, gives you 0. 2 cubed is 8, minus 2 squared is 4, minus 8 times 2 is 16, plus 12. Double check that. 8 minus 4 is 4, minus 12 is negative 12, plus 12, we get 0. Okay, so we know that 2 is one of the zeros. So we're going to divide, let's use synthetic division. X cubed 1, x squared negative 1, negative 8, and 12. Okay, up here in the corner, I know 2 is a 0, so I'm dividing by x minus 2. Okay. So we've got, bring down the 1, multiply by 2, add those together, multiply by 2, add those together, multiply by 2. We get 0, which we should. Remember what this means. This means we took this polynomial, x cubed minus x squared minus 8x plus 12. We're dividing by x minus 2. And what we get is x squared plus x minus 6. So multiplying this over to the other side, we get x cubed minus x squared minus 8x plus 12 equals x minus 2 times x squared plus x minus 6. Fortunately, that's going to factor also. We get x plus 3x minus 2. If we set that equal to 0, our zeros are going to be x equals negative 3, positive 2, positive 2. Negative 3, 2, and 2. So notice we've got a double 0 at 2. Remember what that means. There's going to be a bounce at 2. Okay, degree of the function, x cubed, is 3. Total number of zeros, that's 3. Number of turns, 1 less than the degree, so 2. Remember, that's at most 2. There might be less than 2. Total number of real zeros, well, they're all real. Okay, they're looking for 3, and we found 3 real ones, so 3. And then there's 0 imaginary. Okay, so we can graph our y-intercept. Plugging in 0 for x gives us 12 for y. And then we've got -3 and +2. And remember, there's a bounce at 2. We also know this is odd degree and a positive lead coefficient. Odd degree and positive lead coefficient, our end behavior is down on the left, up to the right. Okay, so we know we're going to pass through this point. We're going to hit this point. We're going to bounce on this point. Okay, so on the left, it's down. On the right, it's up. We've got to go through here. We don't know that that's a max, so let's not assume that. Maybe it keeps going up. Then it comes down here. I didn't draw that great. That's going to bounce at 2 and come back up. It's possible. Maybe it hits this. Maybe it peaks higher up here and then comes back down. Actually, I'm guessing it's probably going to do that. Okay. We don't necessarily know that at this point. Okay, but we're analyzing what we do know. It goes through here. I'm going to guess it goes up here, and on the way back, it comes back and hits here. Then it's going to have time to come over here, hit the 2, bounce at 2. So there's 1, 2 turning points, 3 degree, 3rd degree, and it passes through these points. So we can get a good idea, not perfect, not a TI Inspire. We're not going to be able to graph this thing and see exactly what it looks like. But from analyzing this graph, we can see a lot of things about this function. Okay. Go to the next page. Now, these are kind of fun because we're looking at graphs and then we can determine different things about the function. Okay. How many turns are there? You don't think that should say maximum. There are 1, 2, 3 terms. 3 times it switches direction. Okay. So remember, the number of turns is 1 less than the degree. Okay. At most 1 less than the degree, which means the degree has to be 4 or more. Okay. If it's 3 turns, it's going to be if there's odd number of turns, it's going to be an even degree. So this could be a degree of 4. It might be 6. It might be 8. Okay. Total number of zeros, it matches the degree. So we're going to say 4. Total number of real zeros, well, let's look. 1, 2, 3, 4. Real zeros are actual numbers on the number line that will make your function 0. So 4. If we've got 4 total and all 4 are real, we've got 0 imaginary. All right, let's look at the next one. Maximum number of turns. Well, let's just say the number of turns. We're looking at how many turns there are. So there's a turn. 1, 2, 3, 4, 5, 6. 6 turns. So the least degree of the function, it's at least 7. Because remember, the degree 7, there's at most 6 turns or bumps. Could be 4. Could be 2. Okay. If the function is odd, number of turns, it's even, and so on. Okay. Number of turns is always less than the degree. Total number of zeros matches your degree, so we'll say 7. Total of real zeros, we've got 1, 2. Careful here, that's a bounce. A bounce counts as 2. So bounce is a double 0. Okay, so that's 1, 2, 3, and that's another bounce, 4, 5. So there are 5 total real zeros. Okay, so let's say this is 10, this is -2, and this is -5. Okay, we know there's going to be x minus 5, or I'm sorry, x plus 5 in our polynomial. We know there's going to be an x plus 2 and another x plus 2. And we know there's going to be an x minus 10 and another x minus 10. Okay, I just made those numbers up, so I don't want to put that on there. I was just making a point. We'll see more examples of that. Okay, total number of complex zeros. Okay, so if the total number of zeros is 7, and of those 7, 5 are real, that means there's 2 left. There are 2 complex. Here's how I think about my complex zeros. Okay. how would you shift this function up or down? You could shift it up or down just by adding a constant at the end. If you shifted this up, think about what happens to your zeros. And right now, if this red fancy disco pencil were my x-axis, I would have 1, 2, 3, 4, 5 real zeros. Let's keep going down. What if I go down far enough to hit here? Okay, now I lost that one, but I'd have 1, 2, 3, 4, 5. Okay. If this one dipped a little further, we could possibly have 1, 2, 3, 4, 5, 6, 7. It could count for all 7. When you have a turning point that looks like it's going towards your axis but doesn't quite make it there, that represents an imaginary zero or a complex zero. Okay, so right here you can see, you can imagine that maybe on another function this would go high enough and you could get real zeros, but this one just didn't go high enough, and that's where you would see imaginary zeros. Okay, let's look at the next one. Let's look at the total number of turns. That's 1, 2, 3, 4, 5, 6, 7 turns, which means 8th degree, okay, at least 8. Total number of zeros matches the degree, so 8 and 8. Total real zeros, let's count them. 1 is the double, 2, 3, 4, 5, 6. So 6, and you can see this dip here that almost wants to touch the axis but didn't quite make it. That looks like your 2 imaginary zeros. So 8 total, 6 real, which means 2 have to be imaginary. Okay, let's go to the last page. Oh, we got just a couple more pages. Sketch the following without using your calculator. So we're going to analyze this. So we've kind of already seen this one. 2nd degree, even or odd function. If you multiplied this out, you could see you'd have an x squared. That's even degree. Real zeros, well, 4 comma 0. You could say 4 comma 0 again. That's x minus 4, x minus 4. It's a 0 that occurs twice. Multiplicity of zeros is 2. Okay. You know there's going to be a bounce at 4 comma 0. If we multiply this out, we get x, or actually let's just find the y-intercept by plugging in 0 for x. Negative 4 squared is going to be 16. And then at 4, there's a bounce. We know that the degree is 2, the lead coefficient is positive, so we know that the end behavior is up and up. Okay. Let's look at the next one. Degree of the function, if you multiply this out, you've got x times x times x. That's 3rd degree. Even or odd function, that's odd. Odd degree function. Real zeros will be negative 2, 0, 1, 0, and negative 5, 0. Multiplicity of the zeros, all are odd. So 1, 1, 1, or they're all odd. Okay, we could say this is even over here. Okay. And our y-intercept. So when x is 0, we'd have a 0 there, 0 there, 0 there. 2 times negative 1, negative 2 times 5, negative 10. So we're going to cross there. X-intercepts are negative 2, 1, and negative 5. Okay, 3rd degree lead coefficient is positive, which means our end behavior is down on the left, up on the right. Okay, these are all odd, so we know we're going to cross through here, we're going to cross through here, we're going to cross through here. We have to hit that. I know my end behavior on the right is up, so after I go through here, I'm going to go up. I'm going to go down, pass through here. I don't know if I'm going to go further down after that. I'm going to guess that I do. I don't really know. I don't know how high up I go there, so I'm going to guess. You can't get a perfect graph, but you at least know a lot about the end behavior. You know how many turning points are possible. You know the intercepts. Okay. Let's look at the next one. They're kind of fun to do once you get the hang of it. Okay. Degree of the function, you have an x cubed and another x, so 4th degree. That's even degree. Real zeros are going to be negative 1. I'm just going to say negative 1, 0 with a multiplicity of 3 or odd. And then we've got 3 comma 0, multiplicity of 1, or even. X-intercepts are -1 and 3. Our y-intercept, plug in 0 for x, I get 1 cubed times 0 minus 3, so -3. Okay. It's it's even degree. Lead coefficient is positive. If we multiplied that out, your lead coefficient of your x to the 4th would be greater than 0, which means your end behavior is up and up. Okay, so we know that -1, that's a triple 0. So this one's going to cross through there. Now, it might do something goofy there. We don't quite know. It might almost look like it wants to change its mind and turn, but a lot of times something like that happens. But it ultimately just does pass through there. But it might have some kind of inflection point where it looks like it wants to change its mind and turn around and change its mind and turn around again. Okay, so that one's going to look something like that. Next one, okay, x, and then x squared, and then another x. So that's 4th degree. That's an even degree function. Your lead coefficient is going to be negative, which means your end behavior is down and down. Even degree is either up, up, or down, down. Lead coefficient's negative is down. Real zeros, well, this one is just 0, 0. This one is -2, 0. This one is 3, 0. This one is a multiplicity of 1, or odd. This one's a multiplicity of 2, or even. This one's a multiplicity of 1, or odd. Okay. Y-intercept, so when I plug in 0 for x, my y-intercept is going to be, it's just 0. Plug in 0 for x, you're going to get 0. Okay. Oh, I forgot that. Oh, I have that 0 here. Okay. And then -2, 0. 3, 0. What's my end behavior? Okay, it's 4th degree, lead coefficient's negative, down and down. I'm going to cross through here. I know I'm bouncing off of -2, 0. So on the left, I know I've got to go down. Got to go down here. I'm going to bounce off there. Come back up. I'm bouncing here because that's a double 0 at -2. Multiplicity of 2, I have x plus 2 squared. This one I'm just passing through. 0, 0, I simply pass through. And this one I simply pass through. And my end behavior's got to be down and down. Okay, next one. For the function, x cubed minus 5x squared plus 9x minus 5. Find all zeros, real and complex. State each zero's multiplicity and sketch the graph. Okay, so remember how you do something like this. You're going to check. Possible zeros are plus or minus 1, plus or minus 5. Okay, you could test them all, but I know that 1 works. F of 1 is 1 cubed minus 5 times 1 squared plus 9 times 1 minus 5. Is that right? 5. So that's, yes, 1 plus 9 is 10, minus 10, we get 0. Okay, so we're going to take this thing, x cubed minus 5x squared plus 9x minus 5. I'm dividing by x minus 1. Let's use synthetic division. 1 up there, 1, multiply, add, multiply, add, multiply, add. You should get 0 if it divides evenly. Okay, so when we divide this, we get x squared minus 4x plus 5, multiplying by the x minus 1. So this thing factors into this. So I've got x minus 1, and then does that, I think that works, x plus 5, or x, no, that doesn't work, does it? Two numbers that multiply to positive 5 and add to -4. That's not possible. Okay, so here we have to use the quadratic formula. So we're going to get x equals 1 or x equals 4 plus or minus square root b squared minus 4ac over 2a. So that's going to be 4 plus or minus. That's square root of negative 4, which is 2I all over 2. Divide those by 2. 4 divided by 2 is 2, plus or minus 2I divided by 2. So plus or minus I. So your zeros are x equals 1 and 2 plus or minus I. And let's sketch the graph. And they all have a multiplicity of multiplicity of 1 or odd. Okay, my y-intercept is -5. My end behavior, positively coefficient odd degree, left down on the left, up on the right. And I've got 1 over here with a multiplicity of 1. Okay, so this is goofy. We don't quite know where this is going to happen, but this might have some goofy something happen over here. Might have a couple of bumps looking like that. Okay, we don't quite know. I'm actually curious. Let's graph this one. It could have, yeah, it's x cubed, so it could have 2 bumps. Let's add one to here. Control, add a page. And you get x to the third minus 5x squared plus 9x minus 5. Okay, so I kind of had the right idea. Not too bad. We don't really know what this bump is going to look like, but it does have a bit of a squiggle. Okay, but the y-intercept we had at -5, and then the x-intercept at 1. So this one didn't quite look like that. It was more of a squiggle. Okay, but without a calculator, what I had done the first time would have been perfectly fine. So this function, find all zeros, both real and complex, then state each zero's multiplicity, and then graph the function below. Oh yeah, up here we could write these as ordered pairs, 1, 0. You can write 2 plus or minus I, 0. Okay, even though you're not going to see those on the graph. Okay, for the function, write these. Okay, so let's factor out an, let's see. The function find all zeros, real and complex, then state each zero's multiplicity. Okay, so this one. We have to figure out what might work. And I think -1 might work because it's x cubed. We don't have an x term. We don't have a linear term. We've got a quadratic term and a cubic term and a constant. Okay, so let's take the possible zeros are factors of 4. So possible zeros are plus or minus 1, plus or minus 2, plus or minus 4. I think -1 might work. So -1 cubed is -1. That becomes a positive 1. Minus 5 times -1 squared plus 4. That gives me 0. So I'm going to take -x cubed minus 5x squared plus 4. I'm dividing by x plus 1. And I get, let's do synthetic division, -1, -5, 0 for the 0x, and then 4. I'll put a -1 up there, -1, 1, -4, 4, 4, and -4, 0. Okay, so we get -x squared minus 4x plus 4. Okay, so this thing is going to factor into x plus 1, x plus 1 times -x squared minus 4x plus 4. Okay, I'm going to factor a -1 out of this, so I'll have a negative out front, x plus 1, and this becomes positive x squared plus 4x minus 4. Ugh, That's kind of messy. Two numbers that multiply to -4 and add to +4. Okay, so that doesn't look like that's going to work out. Let's use the quadratic formula. So here x is going to equal -1. X is also going to equal opposite of 4 plus or minus square root b squared minus 4 times 1 times -4 over 2a. So that's -4 plus or minus rad 32 over 2. So -4 plus or minus, that's going to be 16 times 2. So 4 rad 2 over 2. Dividing -2 plus or minus 2 rad 2. Okay, so our x-intercepts are going to be -1, 0, and -2 plus or minus 2 rad 2, comma 0. And how much is that? We can estimate. We've got -1, 0. Our y-intercept is going to be 4. Our end behavior, this is cubic. The negative lead coefficient, so that's going to be, end behavior is going to be up on the left, down on the right. Okay, we don't have any bounces. Let's say -2 plus 2. Rad 2 is about what? 1.4. So 2 times 1.4 is about 2.8. So -2 plus 2.8 gives me about 0.8. So this is going to be -2 plus 2 rad 2. And then I've got -2 minus 2 rad 2. So -2 minus about 2.8 is about -4.8. -2 minus 2 rad 2, comma 0. It's -1, 0. Okay. These are all multiplicity of 1, so we're passing through for each one. After I go through this one, I'm up, I go down, I go up through here. I don't know where I'm going to hit that, maybe on the way down, and then I'm going to go down this way. Okay, up to the left, down to the right, and I'm passing through these 3 points. Okay. Thank you for watching. Actually, I'm going to real quick graph this on the calculator just to confirm. I think that's always fun to do. Let's do control. This is kind of a goofy problem. And you've got -x to the third minus 5x squared plus 4. It looks pretty good, okay? Pretty much looks like what we had right here, right? Okay. All right. Thank you for watching, and I will see you all soon.